Howdy, my name is Kayleigh Curtis. Today I'll be presenting my final research update for my O-REU project titled Ab Initio Database for Machine Learning Potentials, Potential Creation, Validation, and Testing. My sponsors are NSF DMR 1753054 and NSF O-REU, and my mentors are Professor Xiaofeng Chen and Nathan Wilson. Currently, there is no centralized database for storing raw structures and associated properties for MD, molecular dynamic, potential development, and any data that is not stored in a consistent format. The two files shown below are XYZ files, but they do not hold the same information, and they are structured very differently. This makes it really difficult to use data from different sources, since one code that would process a file from one source would not necessarily work for the same type of file from a different source. Overall, these formats lack some desired information that is necessary to train MD potentials. My project aimed to help this problem by creating a centralized database of raw structures that are in a format that can easily be read and processed. I also plan to train a machine learning model with this transform sample data to predict the energy and forces of the structures. To create the centralized database, I created a code that reads the DFT, density functional theory data, and transforms it into a readable format using Python. This makes it easy for the data to be manipulated. This format is used in the generation of fingerprints, which in turn will make it easier to train machine learning algorithms that predict certain materials' properties. A process that my mentor Nathan Wilson has described lays out all the steps in the process that lets you train a machine learning model in order to predict these certain material properties. The steps, in order, are sampling, which is obtaining small samples of different crystalline structures in the larger sample, fingerprinting, which is numerically representing the atoms in the sample, training, which is fitting a function to the provided data in order to predict certain material properties, and benchmarking, which is testing this model against known data to see how accurate the model is. My project focuses on the second and third steps, fingerprinting and training. What this means in terms of a research plan is that we collected DFT data, processed that data into a more readable format, featurized that data, and then trained a machine learning model to predict specific materials properties, in this project, energy. We then compared the calculated energy to the observed energy to see if the model accurately predicted the energies of the structures. To solve the issue of data collection, we created a code in Python that took the raw data, which was a tungsten data at libatoms.org, and transformed it into a Python structure object. Below is an example of what the raw data looks like, what the code looks like, and what a resulting structure object looks like, in order from left to right. These structure objects, which are part of the PyMatGen module, take in all kinds of atomic data and compact them into a smaller, much more easily understandable format. We used this module to create our structure objects, and we added energy to these structure objects so that all of our data ended up in one nice object. After collecting this data, the next step was featurization. What even is featurization? The DFT calculations that the raw data comes from see the entire structure at once, but molecular dynamics, MD, does not. MD sees the local environments around atoms. We needed to convert this local environment into a numerical representation. Below is shown a 2D representation of atoms in some crystalline structure. This atom is the central atom, and this circle represents a true local environment, which are the atoms surrounding the central atom. The problem comes because computers can't deal with just lists of atoms. It doesn't make sense to them, so we need to convert this picture of a structure into a numerical representation. This is the fingerprinting step, featurization, which was stated before. There are many different ways to do this numerical representation, and there are many different studies on which way is the best way, but for the purposes of this project, we just focused on one of the easier methods, the Lennard-Jones potential. We chose the Lennard-Jones potential because of how easy it is to use. This potential requires one variable, r, which is the distance between atoms, and this value can be easily derived from the raw data obtained from the DFT data. There are many different potentials that can be used to featurize this data, and there are many papers about what potential is the best potential. But the Lennard-Jones potential is a good potential to use because there's a lot of data that backs up the validity of the potential. Overall, the Lennard-Jones potential is very simple and easy to use in order to featurize this data. However, the Lennard-Jones potential does have some limitations. It is more accurate in face-center cubic or hexagonal close-packed structures, both of which tungsten is not. For the purposes of this research project, however, this was okay because the Lennard-Jones potential served as a starting point to allow us to get the framework of this code finished. It does have its limitations, but it was a good potential to use as a developmental potential, and later we will implement more complex and accurate potentials into this section of the project once the framework has been completed. This image illustrates the crystal structure of pure tungsten. The numerical equation for the Lennard-Jones potential is listed on the right side of the screen, and it just requires the distance between two atoms. The Lennard-Jones potential calculates the energy of a bond between these two atoms. By summing up the energy of the bonds, we can get the energy of a specific site. and by summing up the energies of all the sites, we can get the energy of the structure as a whole. This numerically represents a structure using only one value from the DFT data, which is the distance between atoms. So what does this mean in terms of this project? Well, I made a code that found all the neighbors of a particular atom within a certain distance, specifically 6 angstroms, and found the exact distance between that central atom and the neighbor atom. Then, we used the Lennard-Jones equation to find the features. After looping this code through every structure, we got a large list of features and their corresponding energies, which is what we needed to move on to the next step, training. What is the goal of training? Training is meant to make a model that can predict the end value that we want without having to collect and process that data beforehand. In this project, that meant that we want to have a model that can predict the energy of a tungsten structure without us having to find that ourselves. This training step involved fitting a function to a part of the feature data that we found. Then, we compared this function to the other part of the feature data to see if the model accurately predicted the energy of the structure. In this project, we are trying to learn the parameters A and B, which are shown here in a differently written Lennard-Jones potential. Epsilon and sigma correspond to specific values that are important to the Lennard-Jones potential. Epsilon is a potential well depth, which is shown in the image on the right side of the screen, and it is a measure of how strongly two particles attract each other. Sigma is the distance at which intermolecular potential between two atoms is 0, and it is shown on the image as well. In other terms, sigma represents the closest that two atoms can get. By modeling the energy data and the parts of the Lennard-Jones potential that we do have, the r to the 12th and r to the 6th terms, we can model what sigma and epsilon are, and once we know what they are, we can begin to predict the energy of these tungsten structures. What were the results? We found that the model did not accurately predict the energies of these structures. For a model that is trained on just the first 100 structures, which are all primitive unit cells, the prediction was poor, and for a model that contained the first 6,000 structures, which contained the same primitive unit cells and much more complex structures, the results were even worse. The second model that contains the 6,000 structures was expected to cause some problems for the Lennard-Jones potential because of the complexity of the structures. We expected this potential to be a decent potential for this modeling, but we did not expect for it to perform this poorly. This performance could be due to a few different things. There could have been an error somewhere in the code that we did not catch. There also could be limitations of the Lennard-Jones potential for these structures. We knew that the potential did have some limitations before we started modeling, but the ramifications of these limitations could be greater than what we imagined them to be. There could also be a limitation in scikit-learn, which is the machine learning package that we used. The scikit-learn optimization method could have found a local minimum, and there could be some underlying bugs in scikit-learn that we aren't able to fix. To summarize, we converted a dataset into PyMat-Gen structure objects, featurized those objects using the Lennard-Jones potential, and trained a model to fit those features. We found that our model was poor, and there are a few specific things that may be causing the issues that we saw. In the future, we want to continue to build this database to include different datasets and different types of fingerprints. We also want to implement cutoff functions in our code. This will enforce a more continuous energy when atoms enter and leave our designated radius. This also reduces cost by allowing for a smaller cutoff radius. We also want to incorporate other structure data into these models, like stress and force data, so we can get a more accurate picture of the structures themselves. Here's the reference to the paper that I got my tungsten data from. And thank you to Texas A&M University for providing me with this opportunity to do this O-REU. And thank you to my mentors, Professor Xiaofeng Chen and Nathan Wilson, for helping me immensely with this project. And thank you for watching.